Hi there. Coming back now to talk some more about the acidity and basicity of substances, and talk about some calculations we do in that. So the section in the OpenStax book we're looking at here is section 14.3, relative strengths of acids and base. You see some learning objectives here. Largely we're going to be focusing on this third one, carry out these equilibrium calculations for weak acid-base systems. To a lesser extent, we'll do some assessment of relative strengths of acids and base through the ionization constants, and even less so the trends in terms of molecular structure, although when you get to organic chemistry, that's the sort of thing you'll do a lot of. So we're focusing on that Bronsted-Lowry definition. We say that an acid is a proton donor. Remember, H plus is proton, and which is, a hydrogen atom that's lost its electron, so it's just a proton. This species right here is called the hydronium ion, H3O plus, and it's basically equivalent to that. And we say that when this equilibrium is a one-way arrow, right, so HA plus H2O arrow H3O plus, and we get 100% of HA becoming H3O plus, that's a strong acid. And weak acids, it's an equilibrium, and they'll yield much less than 100% H3O plus, so there'll be probably more HA left over at equilibrium than there will be H3O plus. Back in General Chemistry 1, we learned about the 6 strong acids and the 6 strong bases. You should know all of those. The 6 strong bases are the strong soluble hydroxides. So if you look at the solubility chart, you'll see these are the hydroxides that are soluble in water. But yeah, you should know those. All right, so if we look at this general reaction for an acid, HA, we can write an equilibrium expression for this, K, and that K, since this is an acid, we'll call it K sub A, which is the acid ionization constant. It's usually always written in a concentration sense, so we have H3O plus here on the top, A minus, and then we divide by HA. And I hope you're remembering that we leave water out because water is a pure liquid. So this is that acid ionization constant. The bigger that is, the more hydronium ion you get, the lower the pH is going to be for a given concentration. So the larger the K is, the stronger the acid. And of course, the smaller K is, the weaker the acid. Okay, Bronsted-Lowry bases now are hydrogen ion or proton acceptors. So you see B, the base here, picking up a proton from water, becoming Hb plus, and then the leftover piece of the water becomes the hydroxide molecule, or the hydroxide ion, I should say. And as before, strong bases give us 100% hydroxide, weak bases much less than 100%. So it's strong bases, it's a arrow, and weak bases, it's an equilibrium. So the generic base equation here for forming that hydroxide ion, Kb for that, lowercase b for base, we're going to have the Hb plus, which is the conjugate acid of the base, OH minus, the hydroxide, divided by B, concentration, and again we leave water out of that because water is a pure liquid and doesn't go on an equilibrium expression. The bigger the Kb, the stronger the base. The lower the Kb, the weaker the base. And that's what's summarized in that slide. Now, if we talk about a conjugate, okay, this is for a conjugate acid-base pair, and as written here, Hb is the acid, B minus is the conjugate base of Hb. If you take Ka times Kb for that conjugate acid pair, it's going to become Kw. It'll be equal to Kw, which is 1 times 10 to the negative 14th at 25 degrees C, which is usually when we'll assume we're working at. And so we can relate Ka and Kb of acids and bases, and we can also relate the acidity of the acid to the basicity of the base. And you see here, the larger the Ka is, the stronger the acid, the smaller the Kb, the weaker the base. So you're going to see tables of these, and we'll talk about those in a minute. What we're pointing out here is that the reaction this way is the acid reaction. The reaction this way is the base reaction of A minus. And if you look at the Ka of HA versus the Kb of A minus, you can predict which way this equilibrium is going to lie. So it's a way to figure out which way a reaction is going to go. This is the case where the A minus is a weak base, and so it doesn't go backwards so much, and it's a stronger acid. Here are a figure from the book on some of the relative acid and conjugate base strengths, and what you see is that the stronger bases go this way, the stronger acids go that way. So H3O plus is the strongest acid that can exist in water, according to Bronsted and Lowry. Its conjugate base, H2O, is a very, very weak conjugate base. Here is a way the table is normally seen frequently, and where you've got the conjugate acids and bases. Frequently you'll see these table, and you'll have maybe the Ka value given for everything here, and you can do calculations based on that. Here is the version that is on your formula sheet for our class, and I want to talk about it just a little bit. So you see acid strength increasing going on that side, base strength is increasing going that way. The strongest acid that can exist in water is H3O plus. So I'm going to draw a line right there. The strongest base that can exist in water is OH minus. So I'm going to draw a line right there. Now, here are strong acids. Here are strong bases, and these two things down here won't exist in water. They'll react and become hydroxide immediately. These are weak acids here. These are weak bases, and then these down here, these are effectively not acidic. They're so weak that they're only there to illustrate how strong the corresponding base is. And up here, these are effectively not basic. Up at the very top. So we can do some calculations for these things. So one of the common ones, for example, is, let's say that we know that the Kb of ammonia is 1.8 times 10 to the negative fifth. What is the Ka of its conjugate acid? Well, can you do as conjugate acid? What's the conjugate acid of ammonia? I'll give you a hint. There's a lone pair on that nitrogen there. So you may remember that the conjugate acid is NH4+. If we look up here, we can see those on our chart here. NH3 is a base, NH4+ right there. See? And so those are going to be equal to, if I multiply those two together, they'll be equal to Kw. So Ka is going to be equal to Kw divided by Kb. So 1 times 10 to the negative 14th over 1.8 times 10 to the negative fifth. And that comes out to be something like 5.6 times 10 to the negative 10th as the Ka of that ammonium ion. So ammonium ion is not nearly acidic, as ammonia is basic. Ammonia's Kb is higher. So it's a stronger base than its conjugate acid is a weaker acid. All right, so what kind of problems are we going to be doing? Well, we're going to be doing things like be given info that to calculate Ka and Kb will be given Ka and Kb in some initial concentrations and be asked to get the pH or asked to get equilibrium concentrations. And pH is a way of indirectly giving you, the pH can basically give you the hydrogen ion or the hydronium ion, I'll say concentration is equal to 10 to the negative pH, right? And the POH is equal to 14 minus pH, and the hydroxide concentration is equal to 10 to the negative POH. So indirectly, pH could give you either the hydronium ion concentration or the hydroxide ion concentration. So we can then calculate Ka or Kb, or eventually being given Ka and Kb, calculate the equilibrium concentrations and the pH. Another figure that folks think about is the percent ionization. Let's see here. Let's just we'll make a problem here. It says previous problem. I don't know what the previous problem is supposed to do. So let's talk about acetic acid. So CH3COOH plus water in equilibrium with hydronium ion plus the acetate ion, okay, AQ liquid, AQ. K for this is 1.8 times 10 to the negative fifth. That same number is the Ka for acetic acid. So the question might have been, what's the pH? Of 0.100 molar acetic acid. So we're going to make our ice chart. It's going to be 0.100 molar here. We won't use water because it's liquid, and we have 0 and 0 here. Q at this point is 0, which is less than Ka, so we're going to say minus X plus X plus X. We multiply those all by 1 because the coefficients are 1. It's clear, obviously, that hydronium ion and acetate ion have got to go up, so even if we didn't know Q, we'd have to know that it had to be plus on that side. And if I make X hydronium ion and X acetate ion, that means X acetic acid has to react. So at equilibrium, I have 0.100 minus X, X, and X. And I can solve this equilibrium problem by saying Ka is 1.8 times 10 to the negative fifth is equal to X squared over 0.100 minus X. Now the way I got that was that's the hydronium ion concentration, which is X, times the acetate ion concentration, which is X, so X times X, X squared. And then on the bottom here we have the acetic acid concentration. So we've got this little math equation to solve here. There is a useful trick here. If you take these two terms, this term and this term, and if I say 0.100 over 1.8 times 10 to the negative 5, if that is greater than, I believe it's 100, then we can say that 0.100 minus X is approximately equal to 0.100. So that's an allowed approximation. And so our equation becomes easier. 1.8 times 10 to the negative fifth is now X squared over 0.1. Much easier equation to solve. X is going to be the square root of 1.8 times 10 to the negative fifth times 0.1. So I want to say that's 0.013. That's 0.1. And that's 0.0013. So So that's our X value. So this becomes 0.013. This becomes 0.013. And this becomes 0.0999 basically. So it doesn't goes down. Doesn't go down a lot. I guess no, I could say that, call it 987, maybe it'll look a little more reasonable. Take one more sig fig there. All right, so our pH at this point, if I take that number, our pH is the negative log of 0.013, and that's going to be 1.89. Okay, now the percent ionization, let's change colors here for a second. The percent ionization, we're looking for the amount of hydronium ion at equilibrium and the amount of initial acid. So in this case, it's going to be 0.013, that number right there, and divided by this number right here, 0.100, all that times 100%. So that comes out to be, I get 13% ionization is what I get in that calculation right there. That's what the percent ionization would look like. If you did a percent ionization problem for weak bases, it's going to be similar. You're going to have basically it's going to be the percent ionization is going to be the HB plus R, the OH minus at equilibrium, divided by the initial I or O initial base times 100%. Where, if we're looking at our ICE chart, ICE, so we're looking at this number on the bottom and this number on the top there is how we would do that percent ionization problem for weak bases. All right, so here's a situation where we're asked to calculate equilibrium concentrations. That's exactly what we did above. See above, we did that problem with acetic acid. We'll do some more of those, so don't worry, we got that. When we look at trying to think about how things are whether they're predicting they're strong acids or strong bases, we look at some things. We look at things like the bond between the hydrogen, that's the acidic hydrogen, and the nonmetal A in this case, and the weaker that bond is, the more acidic that compound's going to be. And so we can look at some periodic trends here. If you go down a group top to bottom, acid strength increases because at the top of the group the orbital size are closer in size. So if I'm looking at HF, that's a weak acid. HCl, HBr, HI are all strong acids. And a big part of that reason is that H is closer in size to the fluorine atom, so that bond is stronger. If you go left to right across the periodic table, electronegativity increases, so that tends to make bonds more polar, which makes things more acidic. So if I'm looking at HCl and H2S and H3 H3P. This is an acid. This is a strong acid. HCl is. This H2S is sometimes considered to be an acid. This is not very acidic. And again, that's because as you go across the periodic table that way, electronegativity increases. So that's an example of that. I have looked at these figures. I've looked in your book. There's no good caption there. I don't know what they're talking about here. Obviously, these are some pH measurements, but they didn't seem to have captioned those, so I can only guess what's going on. They do mention here vinegar, of course, contains acetic acid. We did that acetic acid calculation earlier. CH3COOH is acetic acid. You'll also see that written as HC2H3O2, and if you add those up, that is the same compound. In each case, we've identified the acidic hydrogen as being the one where that arrow is pointing to there. You'll see some abbreviations. You'll see people call it, this whole group right here is sometimes called AC, and sometimes just that group's called AC. So you'll see HOAC or HAC as abbreviations for acetic acid as well. Alright, so here is a case where we've got a weak acid. HNO2 is nitrous acid, and we're given full information about the ice chart. So we know that at equilibrium we have these concentrations. So we could write the equilibrium expression for this, Ka for HNO2 is going to be equal to the hydronium ion concentration times the nitrite concentration. NO2 minus is nitrite. That's a 3 there. And then on the bottom we'll have the nitrous acid concentration. Those values are just given to us down here. So 0.0046 times 0.0046 divided by 0.0470, and if we plug those into the calculator, we should be able to get a value. 0.0046 squared divided by 0.0470, and that comes out to be that Ka is 0.00045, which is 4.5 times 10 to the negative fourth is our Ka for nitrous acid based on the data we have here. If we were going for the percent ionization, we would say 0.0046 divided by 0.0470. So this number and that number times 100%. I have to be careful to make sure I get the right number of zeros in the number. I'm getting a percent ionization of 9.8% for this one. So those are a couple of calculations that we could be doing from those data right there. This is an ant stinging someone, it looks like, or biting someone, and formic acid. Formic acid is this molecule. You see that COOH thing we saw in acetic acid before there. So that's the formula of formic acid, that hurts. That's the sting of an ant. So we have here the formic acid and that's the same formic acid there, HC2OH. And in this problem we were given that the Ka, and this is taken from your book, the Ka is 1.8 times 10 to the negative fourth, and we have our ice chart set up. They had left out the minus x here under the change line, but you see here Q at this point is 0 times 0 over 0.534. That's 0. That is less than our Ka, so that tells us plus, plus, and minus. The x's are multiplied by invisible ones because the compounds are multiplied by invisible ones, so minus x, plus x, we leave water out because water is a liquid. It doesn't factor into the equilibrium expression. So the problem we're trying to solve here is that Ka is 1.8 times 10 to the negative fourth is equal to x squared over 0.534 minus x, and that's representing the hydronium ion concentration, which is x, the formate ion, which is the conjugate base of formic acid, and the formic acid HCO2H, formic acid concentration at equilibrium. Fix that up. HCO2H at equilibrium. Now, we said before that we can make this approximation if this number divided by that number is greater than 100, which it clearly is. We can say that 1.8 times 10 to the negative fourth is about equal to x squared over 0.534. So it's a simplifying approximation that we can make there. So if we work that out, x is going to be equal to the square root of 1.8 times 10 to the negative fourth times 0.534. So I cross multiplied 0.534 over to the left, and then I took the square root of both sides, and then I turned it around so it looks this way. So 1.8 exp4 negative times 0.534 square root. I get that x is 0.003 at this point. So our I'll take one more sig fig, 0.031. So our hydronium ion concentration is 0.0031. That would give us a pH. It's negative log of that hydronium ion concentration. So that comes out to be a pH of 2.51, so pretty acidic. If you get the formic acid in your bloodstream there. We could do the check here, by the way. We could just do a check of our calculations. I'll write a little box here for that. Is Q is equal to 0.0031 quantity squared over 0.534 minus 0.0031. So that's my plugging my approximate value of x there in. And if this approximation is valid, I should get a pretty close value, and I'm actually getting a strange value here. 1.8 times 10 to the negative fifth. That's off by a factor of 10. So I'm not sure if maybe I left a no out there. Let me try that again. 0.0031 divided by 0.534 minus 0. Okay. Alright, so after having run through that check, I've discovered that I didn't make a calculation here. Calculation error, so this is 0.0098, and that again is going to be our hydronium ion concentration. Our pH then is negative log of that. And that's going to be basically 2.01 2.01. My check now, let's run that check again. Q is going to be 0.0098 squared over 0.534 minus 0.0098. And again, I talk about one of my problems is whenever I have zeros like that, I lose count sometimes when I'm punching them in the calculator, so I always look for that problem. All right, so let's see what that comes out to be. 0.098 squared divided by parentheses 0.534 minus 0.098 close parentheses equals, and I get that Q is basically 1.8 times 10 to the negative 4, which is equal to K, which checks out. So my check works this time. So that's why you do your checks. You know, if you make a mistake, it's easy enough moving all these numbers around to make a mistake and have to go back and fix it. So no shame in that, just always good to check it. This is a problem that is strange that it's at this point in the chapter. I think this must have been this PowerPoints must have been made from the first edition, but this is leaning towards a buffer problem, and where we start out with having some acetic acid and its conjugate's base acetate both being present. And the example in your textbook is 1420, and if we plug these values in, so Ka is 1.8 times 10 to the negative 5th because it's acetic acid, and we would have X times 0.1 plus X over 0.1 minus X. And of course that's representing H3O plus, which is our X. Our acetate, CH3CO2 minus, is the 0.1 plus X. And our acetic acid is our 0.1 minus X on the bottom there. The approximation that you can make here is that if X is small enough not to matter relative to 0.1, that means we can leave it out on both the top and the bottom. So we get that 1.8 times 10 to the negative 5th is approximately equal to X times 0.1 divided by 0.1. Well, 0.1 divided by 0.1 is 1, so 1.8 times 10 to the negative 5th is approximately X. So that would be our concentration of hydronium ion would be 1.8 times 10 to the negative 5th. Our pH would be the negative log of that. And that would be 4.74 if you work that one out. The way we're going to work this with the buffers is we're going to use something, and I'll write it up here above it, called the Henderson-Hasselbalch equation. And this is on the formula sheet. It says that pH of the buffer is equal to the pKa of the buffer plus the log of the anion, the conjugate base concentration, over the conjugate acid concentration. And if we think about this, if I've got more, well, first of all, pKa is just negative log of the Ka, and of course for acetic acid, the Ka is 1.8 times 10 to the negative 5th. pKa is 4.74, and that's why I knew the answer to this one without putting in my calculator. That's what you're going to have, the pH, when you've got exactly, if the concentration of the conjugate base and the concentration of the conjugate acid are equal, pH is pKa. And because the log of anything divided by itself is the log of 1, and the log of 1 is 0. Right. Now, if I have more of the acid form, right, so if I have more HA than I have A minus, then what's going to happen is that the log I'm taking here will be a number that's less than 1. So the pH is going to be less than pKa because the log of something that's less than 1 is a negative number. If A minus A minus is greater than HA, then the log's going to be greater than 1, so the pH will be greater than pKa. And remember, of course, as pH goes down, we're going more acidic. As pH goes up, we're going more basic. So that's some good, useful qualitative analysis of this. This equation is one that is on the formula sheet and you will use a lot. So I wanted to show you that one. Okay, here's another one that we're going to work out here. This is the what I guess I would call the bisulfite ion. It's the sulfuric acid that's given up a hydrogen. So H2SO4 gives up, reacts with water, strong acid, hydronium ion, plus HSO4 minus. So that guy is there. This is a very strong acid still. You see the Ka is 10 to the negative 2. That's the largest Ka we've looked at so far. And if we plug this guy in, what we would see is that the Ka here, which again is the 1.2 times 10 to the negative 2, is going to be equal to X times X over 0.50 minus X, which is the hydronium ion times the sulfate ion divided by the bisulfate ion, the HSO4 minus. Now the approximation does not work. So you have to go typically full bore and do the quadratic equation for this guy. The quadratic equation formula is given on the thing. There's a lot of algebra that we can do, but we're going to pick this one up on the next video.